My guest today is Professor Sliman Bensmaia, who is a professor of organismal biology and anatomy at the University of Chicago. His research focuses on how nervous systems give rise to flexible, intelligent behavior, especially sensory processing. That is how our robust and flexible neuronal representations of the environment constructed to support behavior. Welcome, Sliman.
Thank you. Thanks for having me.
Yeah, thanks for doing this. So I want to use one of your older papers to set the context, and we can talk about it more big picture view. But the paper is Intracortical Microstimulation of Human Somatosensory Cortex. You said touch is essential for hand use, yet brain-controlled prosthetic limbs have not been endowed with this critical sense. So in this study, microelectrode arrays were implanted into the primary somatosensory cortex of a person with spinal cord injury, and by delivering current through the electrodes generated sensations of touch that were perceived as coming from his own paralyzed hand. These are people with spinal cord injuries, and you are connecting this electrodes directly to the brain in this case, or what's happening here?
Yes. I mean, maybe take a quick step backwards and think about why are we doing this before we talk about exactly what we're doing, right? So, sure. I mean, the idea is, anytime we interact with objects, here's my phone, right? We get, we're sending all these signals to our muscles to move our hands, but we're getting, this barrage of sensory signals back from our hands to tell us about the object. So I know the shape and size of this thing that I'm holding, where its edges are, and that, those sensory signals are critical to supporting our interactions with objects. And if we lose those sensory signals, even with an intact motor system and muscles and everything, we, lose our ability to really interact, effectively with objects. So that's sort of the premise of this work. And so now we're working with different people who have lost, their hand use, right? Either because they've lost their hands or because they suffered a spinal cord injury, and the connection between the nervous system or the central nervous system and the hand has been compromised. And so for these subjects, and now as I think people have been exposed to this, there have been developed these bionic hands, right? So these bionic hands can either be controlled via residual muscles, the muscles of the arm. Most of the muscles that control their hand are actually in the forearm. So you can use signals from these muscles to actually control this bionic hand for amputees. And in the case of spinal cord injury patients, that tetraplegic patients who are paralyzed and insensate from the neck down, you can use signals from the motor parts of the brain, right, to control it, right? So now what we work on is to restore the sensory feedback. And so for amputees, we can restore the sensory feedback by electrically stimulating the residual nerves that used to innervate the hand. And for tetraplegics, that nerve is no longer attached to the brain. So there we actually stimulate directly the parts of the brain that receive these sensory signals. And the paper that you're talking about there, Intracortical Microstimulation of Human Somatosensory Cortex, is the first study showing. So we had done studies prior to that with monkeys, showing that with monkeys, you could evoke tactile sensations by electrically stimulating the somatosensory cortex. So again, somatosensory cortex is the part of the brain that receives the part of the cerebral cortex that receives these touch signals from the body, right? So anytime you feel something, there's a little activation in the somatosensory cortex. And if you electrically stimulate, and what we show in this paper is if you electrically stimulate the somatosensory cortex, you can evoke these very vivid touch sensations. And what was cool is we knew we could evoke some touch sensations from monkey work, but this was the first time where we showed, where we could ask a human, what does that feel like? And the human said, well, that actually feels like pretty natural touch. It's like the type of sensation that I might experience if I interacted with an object.
So for a normal person, when we move our arms, move our hand, there is some sort of an electrical signal traveling to the brain through the spinal cord.
That's right.
And I guess when you have an intention to move your hand, there is some sort of a signal coming back to the muscles to actually make that happen, right?
That's
Sort of for a person that is a spinal cord injury, that connection is now lost. Brain is okay, hand is okay, I would imagine,
yes.
able to create the signals, but the signals cannot travel to the brain, nor can the brain instruct the hand to
That's
move.
right.
And so what you're proving in the paper is that if you stimulate the hand in this case,
Well, you're stimulating the brain.
or stimulate the brain, okay.
Yes.
And how do you do that?
Well, so in this case, there are different approaches, but there's only one that's actually approved for human use, and that is these arrays of electrodes developed or manufactured by BlackRock Microsystems, I think they're called, and they're arrays of electrodes. They're like 4 millimeters by 4 millimeters, so very small, and the electrodes themselves are about 1 to 1.5 millimeters, depending on which one you use. And there's 100 electrodes over this 4 by 4 millimeter array, and you just punch this array into the sensory parts of the brain, or the motor parts. You use the same arrays for the motor, reading out motor signals, or electrically stimulating, the somatosensory cortex. And then this involves doing a small craniotomy, a fairly large craniotomy actually, putting these two arrays in, and then putting the skull back. And somehow that it does not damage the brain, and you can record signals for many years using these arrays.
But how will those signals travel back to the muscles though, since the connection?
Well, so that's a great question. The stuff that we do involves not restoring movements of the native hand. It involves controlling a robotic hand. So here, what we're doing is we're reading out signals from the motor parts of the brain that are essentially intact, right? And then, there are sensors on this robot, and then using these signals to move and control this robotic hand, this robotic arm and hand. And then there are sensors on the hand, and we take the output of these sensors and to drive the electrical stimulation of somatosensory cortex, right? And so this is all robotics. Now there's a different path, a very challenging path, which is to then use these brain signals to electrically stimulate the muscles to reanimate the hand, right? And that's a different strategy. And that's a great strategy, except it's hard enough to infer, intended movements from this part of the brain, and then to restore touch with a robot, that's pretty hard. And now, if you want to reanimate the muscles, that's even harder, right? So I think we're kind of a step toward that.
So that is when you have the spinal cord injury. Suppose you don't have a spinal cord injury, but you actually lost the hand, let's say.
Right. Mm-hmm.
So you have a bionic hand put in that position.
Yes.
And presumably it can generate some electrical signals mechanically or some artificial ways, and then send that to the brain in that case, and then get some connection back.
Yes. So the strategy that has been adopted for amputees is one where you just don't interface with the brain. You interface with the nerves and the muscles, right? So again, if you move your hand, there's a pattern of muscle activation in your forearm. And so an amputee, the hand is no longer there, but they can still produce these patterns of activation in the muscles, right? To the extent that these muscles are still there. And so what you can do is put sensors on the forearm to read out what the amputee is trying to do, and then make the robot do that, right? And what we do, and to restore the sense of touch, well, there's a nerve, that comes from the spinal cord and innervates the hand. Well, that nerve is fine. And so what we do is put little electrodes, chronically implanted electrodes in the nerve, and then you electrically stimulate the nerve, and poof, it's like you get these sensations that are very vivid sensations coming from the hand that is no longer there.
So I don't know much about this, Sliman. So if let's say there's an intent in the brain to move the hand, it is sending some signals through that nerve but it cannot reach the hand because there is no real hand there, but there is a bionic hand, right? So could you collect those signals and then transform that into a mechanical motion by using some sort of an algorithm?
Absolutely. That's one approach. I mean, you could completely, in principle, you could put electrodes and read out intended movements from the nerve. And in fact, people do that to some extent, right? But to the extent that you still have these muscles there, these muscles are amplifiers for these neural signals coming from the brain. And so it's much easier to read out these signals from the muscles than it is from the nerve. But in really what you're doing is reading out the signals from the nerve through the muscles, right? But I mean, that it's, conceptually, it's the same idea. It's just in terms of, implementation is easier. It's just, muscles make these huge, much stronger signals than nerve fibers. Nerve fibers make signals on the order of hundreds, of microvolts, whereas, muscles are much stronger electrical signals.
So I want to go back to the spinal cord injury part. So you have electrodes going into the brain, you're stimulating the brain to some level. And so what happens then? I guess I didn't quite pick up. So let's say you're stimulating it artificially, some brain areas, the motor parts of the brain. And then what happens?
Well, actually, you're stimulating the sensory parts of the brain.
The sensory parts. Okay.
You're reading out signals from the motor parts of the brain, and then you're pumping signals back into the sensory parts. So, here's a sort of a crash course into, sensory neuroprosthetics, right? So, as most people know, at least everyone in neuroscience knows, right? You have a map of your body and your brain, right? It's called the somatosensory homunculus. So there's a part right here that responds to the hand, and another part here that responds to the face, and there's a part here that responds to the trunk. And so, every part of the body, there corresponds a part of the brain that really kind of represents that part, or that responds when that part of the body is touched and gives rise to a sensation that's appropriate to whatever part of the body, right? So if I touch your hand, you feel something on your hand, right? That's because there's a specific part of your brain that was activated. So what we had shown already with monkey experiments, but what this study that you mentioned earlier in Science Translational Medicine really showed in a human, is that if you put this array in the hand, so the part of the somatosensory cortex that receives input from the hand, that received input from the hand before the spinal cord injury, let's say you stimulate an electrode that used to respond to the index finger. I mean, like you electrically activate a part of the brain that used to respond to the index finger before the spinal cord injury. You give rise to a sensation on the index finger, right? And then if you stimulate it, through an electrode and activate neurons that used to respond to the thumb, you give rise to a sensation on the thumb. So now what you can do is you can connect the sensor on the prosthetic hand, the thumb sensor on the prosthetic hand, to the thumb part of the brain, the index sensor to the index part of the brain, and now every time the subject touches something with the thumb and index fingers on the prosthesis, you electrically stimulate the thumb and index finger representations of the brain, and you give rise to a sensation as though the thumb and index finger touch something, right? So, and what, a more recent paper that came out, I was not a co-author on it, but my colleagues at University of Pittsburgh showed that when you do this, subjects become much better at interacting with objects and grasping and transporting objects, right? So that study that we did together was a study that showed here's the perceptual experience of electrical stimulation of this part of the brain, somatosensory cortex. And then this new study shows that if you do what I just described, connecting sensor on the prosthesis to these sensory representations of the brain, people become much better at using these bionic hands. So that's a very promising first step.
Yeah, so touch is a really important thing, and it's a very complex thing, I would imagine, right? So, so this idea that we can sort of do that electronically. Now, the problem here is the complexity in the wiring, right? I used to be an engineer, Sliman. You look at automobiles and aircrafts, you can see how bad the wiring is in those things. Engineers do a bad job in industrial design sometimes. But nature seems to have done a pretty bad job here too, right? It is the wiring is really complex, so as to disallow replication in some ways.
Well, I mean, I would disagree with that statement that nature has done a very bad job because, with all due respect to your engineering friends, the brain is the most complex system in the known universe and is capable of, flexible, intelligent behavior in a way that no artificial device can. You can take the best robots, the best robots in the world can't even come close to doing what brains can do. They can be specialists at chess or specialists at, I just saw the Boston Dynamics robots can do parkour. That's amazing, right? But, doing all the things that human brains can do. But you take a robot and you put it in a novel environment that it wasn't trained for, and that robot is going to break down catastrophically. Whereas you take a rodent and put it in that environment, and the rodent is going to do some stuff. It's going to try to figure it out, right? And so, the brain is an incredibly powerful thing, the nervous system in general. Now, it is so complex that trying to reconnect it when those connections are broken, that's true. That's hard to do. But that's just not what, through evolution, if you had a spinal cord injury, you would die, and that's okay. There'd be other people there to continue the genetic line. So I think that was just not the goal, right? The goal is not the individual. The goal is to,
Yeah, I guess that's an important point. If you had an amputation, if you had a spinal cord injury, you would not have survived from an sort of evolutionary perspective. There was no reason for you to survive, and hence there is no design change.
That's right.
But purely from a design perspective, it seems highly risky, the spinal cord design, right? If you bring everything together into a singular sort of a tube going up and to the CPU, and you break it, and the whole thing comes down. But I guess it should have some other evolutionary advantages, I would imagine.
Well, I also want to point out that it's pretty hard to have a spinal cord injury, right? And you have to have a vehicular accident or do something really kind of dangerous, for that to happen. And so, these are things that are now possible, but were not possible even, 100 years ago. So, I've never thought about this, but you bring up a good point. That my guess is that spinal cord injuries have become much more prevalent recently. I guess there were horses. Horseback riding can probably cause, severe spinal cord injury.
Still, from an evolutionary horizon perspective, it's still too narrow a time frame, right, to have any effect.
Yeah, right. Yeah.
So I want to go into your latest paper. Chronic use of a sensitized bionic hand does not remap the sense of touch.
Right.
What do you mean by that?
Right. So this is kind of well, let me tell you a story. Let me tell you a story about this. There's this idea that the brain is this very labile plastic thing that you if you expose it to something. If you expose the brain to something enough, it'll sort of learn it, right? It'll just learn it. And, it's been sort of I think that people overestimate the degree to which that's true. Absolutely, the brain is an amazing learning device. And there's certain things that it can learn, and then there's certain things that it can't, right? Anyways, I can go through a bunch of examples, but the key one here is about sensory representations. There was this idea that you lose an arm. So now there's a big part of the brain whose job it was to represent that arm. And now we can just use that to do other things with it, right? And, so then I have my colleague, Max Ortiz-Catalan. He's at Chalmers University in Gothenburg, Sweden. And I was revisiting him 6 years ago. And the problem is, you implant these electrodes in the nerve. but the nerve is the nerve, and you don't, you just stick these electrodes in the nerve, and then you get what you get. So you electrically stimulate, and maybe you'll get a sensation for electrode 1 on this part of the hand, electrode 2 on this part of the hand, electrode 3 on, you have there's no way to know in advance or to surgically target these electrodes to hit specific, fascicles associated with specific parts of the hand. And the problem with that is that 90% of our interactions with objects happen with the fingertips, right? So you really want to hit the fingertips. And so Max had say, well, he knew this, right? He knew this was a problem 6 years ago. And he was like, well, what I'm going to do is I'm going to, do my best, get as close as I can. But I'm going to map the sensor on this prosthesis to the closest, nerve fascicle that I can get to the thumb, and the index to the closest fascicle to the index, etc. And what I expect will happen is the brain is going to learn and remap, so that now, eventually after chronic use, touching the thumb will feel like a sensation on the thumb, right? And then 6 years later, Max happened to be in Chicago, and he was like, I owe you a 6-pack of beer. I was like, that sounds good, and I'm all in, but why? And it turns out that I had bet him that would not happen. And, because that is not the kind of learning that the brain does. When we hit adulthood, there's no reason for these sensory representations to remap. Like we talked earlier, if you're an amputee, and through evolution would, a biological system to evolution wouldn't be like, well, let's repurpose that part of the brain. Most amputees died. If you lost an arm, you would die up until just a few hundred years ago. And so there's no kind of evolutionary pressure to kind of create a system that is going to repurpose deafferent parts of the brain. So that was my kind of reasoning. Anyways, and I was right. 6 years later, Max comes and owed me a 6-pack because, there were what he showed in this study is, so there was a sensor on the thumb that elicited sensations, say on the thenar, and after 2 years of seeing the thumb touch things and feeling a sensation on the thenar, the sensation never moved. It just stayed right where it started, right?
Yeah, that is really interesting. So, we hear a lot about, like you say, brain plasticity, its ability to sort of rewire itself,
Yes.
learn things. It seems like there are two types of learnings, though, right? Neuroscientists don't like to use any sort of computer analogies, but there is a difference between sort of software learning, meaning you can pick up a language, you can pick up music, play guitar, to hardware based learning. And as you say, if the brain sort of specialized to different parts of the body, and in the past, if you lost critical limbs, you're not going to survive. It seems like from an efficiency perspective, they're sort of hardwired without a lot of flexibility. Is that what you're saying?
I think I love the computer analogy, but sometimes it breaks down. And I think this is the case where it breaks down, right? I think the same kind of learning in principle could happen in both, right? Like the kinds of learning that you would see in a sensory system that we're talking about might be the same kind of learning that you would need for language, right? In principle, the same kind of implementation of learning through rewiring of neural connections could happen for both, right? But I think that there is different susceptibilities to learning of different parts of the brain, right? Whereas in these early sensory parts, they're sort of, after you hit, puberty and your body stops growing and changing, those parts of the brain just stop being labile, right? Other parts of the brain, generally, unfortunately for us old guys, at least for me, old guys, I won't speak for you, our ability to learn is severely diminished, like good luck learning a language or learning to play an instrument after the age of, 8, basically ish. I mean, some people manage to maintain that ability beyond that, but most people don't. So in fact, learning is somewhat limited, right? You can tweak things, but you can't just start a new thing from scratch, that old, like that there's like that door closes during what's called after the critical period, which happens, in teenagehood. But, let me give you an example. Here's a thing that we're working on, but that gives you a sort of a sense of the lack of plasticity. This is, we haven't vetted this completely, so this is kind of hot off the press kind of result. But so, it might turn out not to bear out, but I think this is true. So one of the projects we're working on is called the Bionic Breast Project, and it's for women who have undergone mastectomy. They scoop out all the tissue, including all the nerves, and so these women end up being completely insensate in their chests, right? So we're working on trying to restore sensation for women who have undergone mastectomy, but using the same technologies that we've been talking about, except instead of stimulating the nerves that innervate the hand, we want to stimulate the nerve, put a sensor on the in the nipple areolar area, and then stimulate the nerves that used to innervate the chest, the intercostal nerves, right? So, in the process of doing that, we want to study breast sensation because we don't know much about it. What are the nerves? What is the type of, tactile nerve fibers that innervate the chest? Very little work has been done on that. So we're doing that work. And in the process of doing that work, we discovered that, the brain representation of the breasts is distorted because the breasts develop pretty late in life, right? And they start growing pretty late in life, and therefore the brain, by the time the breasts come in, the brain just is not plastic enough to adjust to that different sort of morphology of the chest. And so women, when this is a subtle effect, it's not like they have a complete no idea what's going on, but the maps of the breast are somewhat distorted, and this effect is greater for women with larger breasts, right? So that's just, I think, another kind of a testament to how the brain just can't keep up with that kind of body change beyond, puberty.
How does it work, Sliman? So when you grow, the brain has to sort of proportionately adjust your scale, right? You're increasing your height, you're increasing your weight.
Yes.
You sort of redoing your map, so to speak.
Mm-hmm.
That seems to be programmed in, right?
Right. So I think, again, I'm not an expert on these issues, and I'm not sure to what extent people have studied them carefully. But what I will tell you is that what is known, and this is not just for touch, this is across the entire brain, right? The ability to learn new things. I mean, young people are much more plastic than older people, and that involves, and there's a variety of ways in which that's true. Like young people have a lot more neural connections, and a lot of these neural connections are pruned through the critical period. So we actually have less neural connections in our brains, right? What you want to do is you just preserve the neural connections that are useful and get rid of the ones that are not. And that sort of happens in the critical period. And there's other things that I'm not probably, that I don't know about because I'm not a developmental neuroscientist. But one thing is, that I do know is that during that period, we are much more plastic and much more labile in our representation. Like you said, just sort of adjusting with the fact that our bodies are changing and growing. The distance between our eyes is changing so that, the visual system has to be able to adjust for that. And then there's one day we grow into adults and the brain, says, okay, this is it. We're done, And that makes sense because imagine if you were really plastic all the time. If I put my elbow down on this table for 2 hours, I don't want the elbow representation to suddenly become the biggest representation in my brain just because it's so active, right? You want to have the sensory system being a kind of a ground truth of your body state. And once your body stops changing, there's no reason for those representations to, the mapping between the body and the neural representation or the neural, activation to change, right? Anyways, I mean, that's, and I don't want to overstate it, it can change a bit, but some people thought it was like this magical, it's like pixie dust. just everything could be fixed with plasticity, and that's the part that I've been sort of actively sort of uh, um, working against, kind of this naive view.
So this idea is true for animal models too, right? So I was doing a thought experiment. So suppose you have, let's say, mice models or something like that. You, I don't know if it's possible, Slim. I'm just throwing it out there. Let's say
Mhm.
you don't feed them. They're severely malnutritioned
Okay, we
during
would
their
never do
during.
that. We would
Huh?
never do that. But go on. Yeah.
If it is possible, as a thought experiment, so during their, sort of the growth period, they don't actually grow much.
Hmm.
And then when they are adults, you feed them
Hmm.
really well. And then suddenly, they put on it to a higher frame. Do you think we will see a big difference in the brain?
Well, first of all, I just want to point out that that happens to most of us, right? In adulthood, we grow a little bit more than, we still grow. We still continue to grow. And I think, again, it's like the breast idea, the breast example I gave you earlier, right? No one has done this research, but I'm pretty confident that somebody who gains an enormous amount of weight in adulthood, right? I mean, and basically all of us to some degree, but the more weight you gain, the more your brain's representation of your body is going to be distorted, right? It's going to sort of like, however your skin stretches and distorts as you put on weight, your brain is not going to follow that. And that would be an interesting kind of a follow-up study to do on this breast, study that I mentioned to you, is that I think that people that gain a lot of weight probably have these slight, mismatches in their sort of body image in their brain.
How would you measure that? Um,
Right, that's a great question. So what the study we're doing um, for the bionic breast is you blindfold the subject and you touch the breast in two different spots, along a line, like a vertical line, right? And you ask the subject whether the first touch was above or below the second one, right? And like on the hand, you are very good at that, But on the breast, there's certain patches of breast where you're very good at that. You know which part, the relative positions of that. And then there's little patches where you get it wrong, systematically wrong, right? Where you think this patch is, below this patch systematically, right? And that only happens on the breast. I shouldn't say it only happens on the breast. Of the places we tested, the hand, the back, and the breast, it only happens on the breast, and it's more pronounced with women, for women with larger breasts.
so you could do the same thing with the people who have gained a lot of weight.
Yes,
Same
that's
sort of
exactly right. Exactly, that's right. I mean, I didn't have that idea until earlier until this conversation, but that is definitely a thing we could do, and maybe a thing we will do. I have a lot going on, but maybe a thing we will do.
because it does, well, presumably it has some implications for sort of therapeutic interventions, right? So if you have sort of a distorted map, um, wouldn't you? I mean, supposing you are successful, with the bionic arm and all the things that are happening in that arena, it sort of assumes that you have a sort of a precise way to interact with the brain, right? If there is distortions in there, I would imagine you'd be less successful.
No, that's absolutely true for the hand, right? If every time you touch it, you touch something with your thumb, you feel it on your pinky, that's really bad. And that's going to have a major impact on your ability to interact with stuff. Fortunately, though, the breast, the chest, or the belly, where the other people might have adulthood growth, it doesn't. These are very subtle distortions, and they're more interesting from a scientific standpoint than they are. I don't think they have any real implication, right? Because it's not with your breast. You're not doing a bunch of complicated stuff. It's like, and probably, and the same thing is true with your belly, right? So I don't actually think this is a serious consequence. I think this is an interesting consequence of the lockdown of sensory representations in adulthood. Again, I just want to point out, though, remind you that this is somewhat speculative. I mean, these things about, and need to bear further scrutiny.
Yeah, so I'm thinking back to your colleague in Sweden and the bet that you won.
Yes, I won that bet.
And so it basically says that you can't really rewire. When you lost it, you have lost it. It's impossible for the brain to learn sort of a new sequence of things. It's sort of counterintuitive without knowing anything about it, Sliman. I used to think the brain, like you say, it's pretty plastic. So if you keep repeating the experiment, do we know how many times? So suppose you do it, you keep repeating the experiment 1,000 times, 10,000 times, a million
Well,
times.
that's the thing, though. The thing that's beautiful about Max's study is that these people went home with this bionic hand and used it for a year or two, right? Every day they used it. Hundreds of times they interacted with objects and had this sensory mismatch, and there was no rewiring, right? And again, just to be clear, there is still a full body representation in the brain there, right? It's actually, that hasn't changed at all. It's and the mapping between the nerve and the brain hasn't changed at all, right? And cannot change. So there's nothing wrong with the wiring. It's just that we can only access part of the wire, and we're stuck with that. We can't, we can't hope that the brain is going to help us along, or that the nervous system is going to help us along. If we get a palm sensation, it's going to stay a palm sensation, right? And that's unfortunate. I mean, from this perspective of neuroprosthetics, it would be great if you can just stick electrodes and it doesn't matter where the sensations are initially, because you can always kind of, move them to wherever you need them to be, especially the fingertips, right? Because again, it is so important. When I grasp this object, I can feel that my pinky is touching it here, my ring finger is touching it here, my thumb is touching it there, and that is a key, contributor to my ability to interact with this object as flexibly and dexterously as I can.
Could you do some sort of a trial and error type thing? So suppose you deploy machine learning type techniques, right? You're picking up a lot of data.
Mm-hmm.
And what the data is saying is that it's not right. There are errors between what you expect, what you expected, what actually happened.
Mm-hmm.
That type of data might allow you to sort of incrementally improve it over time, couldn't it?
Right. No, that's true. I mean, that is a possibility that we did not test, or that Max didn't test, is maybe it's too much to ask the nervous system to go from here to here, right? Maybe what you want is first move it here, then here, then here, then here, and then gradually. I think that's possible. That's the kind of thing where maybe we can, there is some plasticity, we can channel whatever, harness whatever plasticity there is. But the thing we can't do is create maps de novo in adulthood. But we can maybe tweak things, and if we tweak things incrementally, that might work. I mean, that's again totally speculative, right?
Yeah, I mean, it's an interesting thing because the therapeutic approach, if you take the hypothesis that the brain is not able to rewire, as many people seem to hold, then the approaches that you might take for intervention are quite different because you have to mechanically adjust. So you have to basically look for incremental, maybe some AI-based techniques. Let the machine figure out incrementally what the optimum configuration might be. You take the brain as a given, and don't try to train it, but you might be able to train a machine to incrementally model the brain on the hand.
Yeah, I mean, that sounds cool, and AI does all kinds of cool stuff. But this is unfortunately not one of those situations. Here's on the output side, it might work better, right? You have muscles, you have signals from the muscles, like for the amputee, or from the brain for a spinal cord injury patient, and then you're using these to infer what the subject is trying to do, right? And that's a place where AI might help because, for instance, like the muscles that control the thumb, a lot of them are in the hand, right? And so, and so they're definitely gone after amputation, right? And so maybe you can, use AI to infer more precisely what the intended movement is of the thumb based on what the other muscles are doing. So that's a place where maybe it'll work. But on the sensory side, it will not work. And it will not work because what you have to do is pump into the brain signals that are interpretable. Imagine this. We have 17,000 nerve fibers that innervate the palmar surface of the hand, the glaber surface of the hand. Anytime we interact with an object, we're getting this barrage of 17,000 different signals coming all at the same time. And we, effortlessly and unknowingly interpret these signals, and we can tell the shape, the size, the texture of an object, its motion across the skin from this incredible amount of information that we're being bombarded with. And that's because the brain, you're sending signals that the brain knows how to interpret, right? And that's why, this is something that hasn't come up yet, but that is the guiding principle in this. Is to make this work, we need to be able to speak the language of the brain. And so we need to understand, how does the nerve convey information? And if we could replicate exactly what the nerve does, we would completely restore touch in all its glory, right? We don't have the technology to do that, but what we try to do is come as close as we can to that. Come as close as we can to, reproducing the signals that would be produced in the nerve given a specific interaction, right? And that's sort of, this is called the biomimetic approach that guides all our work.
Yeah, it seems like a really difficult problem. Yeah, but there is often there is a macro intent, right? Suppose I say I want to pick up this ball to move it from X to Y. Mm-hmm. If it's a human experiment, the human can say that is the macro intent.
Yes.
The brain has to take that and then split that into a variety of instructions.
Yeah.
And then ultimately convert that into a large amount of electrical signal. Yeah. Mm-hmm. But if the data is available in sort of a hierarchy in that fashion, wouldn't we be able to sort of teach a machine at some point?
Yeah, right. So I think there is, so what we do is kind of, not work with what you're calling a macro intent, but really work with the low-level signals that are sent to the muscles or that are in the muscles, and then the sensory signals that are sent back to the brain at the early stages of processing, right? Either in the nerve or in the brain. There's another approach that consists of, let's not mess with the muscles. Let's just figure out what the subject wants to do and make the robot do that, right? Not say, okay, move this finger and that finger, but say, hey, pick up this object, and then just get the robotics to do that for you, right? And that's, it's a cool idea. The problem with that is that you have, it's almost like a lookup table. You need to have, in order to reproduce what hands can do, you need to have like thousands and thousands of potential actions, right? And so that's not that's not impossible to do, but you have to then be able to from these brain signals figure out which of these thousands and thousands of potential actions. The reason why the approach that we're and for that, and one cool thing, so my colleague Richard Anderson at Caltech really kind of takes that approach to some degree. And there you're actually, instead of interfacing with the motor cortex and somatosensory cortex like we do, which are low-level kind of areas in the brain, you actually want to interact with higher-level parts of the brain. Parts of the brain that have goals, like big picture goals, like pick this up or move over here, right? And so why I think our approach is more promising, ultimately, look, just full disclosure, our approach involves the parts of the brain that I'm an expert on, and his approach involves parts of the brain that he's an expert on. So we, it's like different approaches, and but the advantage of our approach is that it exploits the combinatorial nature of sort of these low-level representations, right? If you have a thing that controls the thumb, and a thing that controls the index finger, now you can do all kinds of things with the thumb and the index finger, right? If you're saying, pick up a sphere, pick up a block, pick, punch this guy, or whatever other, flip this guy off. These are, that's, you really have, those are not combinatorial, right? You just have to have, look up table of these different kinds of actions. And unless we come up with a dictionary of action, and some people are thinking about, are working toward that, it lacks that combinatorics that I think is the advantage of using these low-level representations.
Yeah, so these low-level signals also has some time dimension to it, right? It's not, there is some delta t beyond, the actions, right? So I wondered, as those signals come in, suppose, we get computing power continues to increase. We have quantum computing, or whatever the case may be. We can look at data at much higher levels than we currently do. Those sort of time-wise changes could be learned, right? In other words, there should be patterns in that low-level signals. Humans are notoriously predictable. They do things over and over again in the same way. If you buy that, then the low-level signal patterns would be repeating. In other words, an AI agent can forecast or predict what the human is likely to do at t equal to 0, what POC is likely to do at t equal to 1. In which case, you can really remove the latency in those processes.
No, I hear what you're saying, and actually, there is a very influential movement in motor neuroscience. Primarily in motor neuroscience. I mean, it sort of has some impact in other places too, but mostly in motor neuroscience. That is the dynamical systems approach, right? Which is, as you said, in the nervous system, it's slightly different than what you said, but it has to do with time, right? The brain consists of these 100 billion neurons that are interconnected, and so the activation of one neuron. Each neuron is activated by other neurons. That's the way the brain works, right? And so you have these patterns, these sort of predictable patterns of activity in the brain, right? Where if you activate this neuron, it's going to have a specific, influence or cascade of activity after that. And there are now mathematical approaches that have been developed, dynamical systems analysis, and sort of like, especially tailored to the brain and to neural systems, to try to understand how these dynamics of the brain evolve over time, just like you said, so that you can now look at a given time, a period of time, and then predict what's going to happen next, basically in the brain, right? And so, except that I disagree with so that's a useful tool to understand. Because that constraint, there's a constraint in time. Like whatever's happening at time t makes time t plus 1 more predictable, right? But we're talking about 100 billion neurons. Like the hand itself, is only one of the many things that we do, but it's definitely the most sophisticated effector out there. The hand itself, operates in at least 30 dimensions, So you're controlling this 30-dimensional end effector. And so even the predictability, the predictability is still pretty high dimensional. It's not predictable enough, I think. I mean, again, I guess, the reason I'm putting it this way is because there was this idea that the hand was actually much simpler. Because if you do principal components analysis on hand movements, 90% of the variance in the hand movement can be explained using 6 principal components. So then it's like, well, the hand is only 6-dimensional. But the last 10% of variance in the hand movements is also super important. It's why we're good at using our hands. Otherwise it'd be like a mitten kind of thing, right? So, you can pick things up with a mitten, but you can't play piano with a mitten. And so the idea, so that's why, that being said, that's why I was kind of phrasing this negatively, but in fact, this idea of dynamics and using the sort of the predictable aspects of brain activity can constrain our can constrain the models that map the neural activity to behavior and are now being deployed to do that. And I think that's a great point.
Yeah, I mean, this field is really advancing along with computing. And it seems like as we look forward, there are a lot of interesting opportunities. So in conclusion, what are you most excited about? If you look forward 5 years, where do you think we will be in both of these areas, the spinal cord injury or loss of a limb? In both of those areas, where do you think we will be from a practical, useful implementation perspective?
Right. So let me just say one thing that hasn't come up yet that's very important. The bottleneck is not the computing. I mean, the bottleneck is the neural interfaces themselves. We have neural interfaces that are only, we have 100 billion neurons in the brain. I mean, we're maybe interfacing with like 100 or 200 of them, with these things. So that is just woefully inadequate. Also, actually, it's surprising how well we do with such a small, a sort of low bandwidth signal. And then the second thing is that they don't, especially the brain ones, don't last. They only last 4 or 5 years. You can't ask people to have a craniotomy every 5 years. And I think that's one of the major problems major challenges is to create interfaces that last, decades for the rest of your life, right? So the computing is not so much the challenge as is the neural interface. As the neural interfaces improve, computing may start becoming the bottleneck. And there are people working toward that. For example, the most famous of which is Elon Musk's Neuralink, right? He has this fairly sophisticated robot to put in a bunch of electrodes in the brain. I mean, and while his, public statements are a little bit over enthusiastic and ambitious, I think that the team of people who are working on it are excellent engineers and neuroscientists, and I think they're doing some pretty cool stuff. Whether it meets the goals or not is an open question still. In terms of the neural interfaces, I think the peripheral nerve ones are getting to the place where they could be clinically viable, for amputees, could be clinically viable devices soon. For the brain interfaces, for the reason I just told you, it's not clear what the timeline is. But what I will say, just to plug our work, is we're working with the University of Pittsburgh folks to create more dexterous prostheses. Really trying to do a deep dive into how the brain controls a hand. The prostheses up to now, the brain control prostheses have been good at controlling arms, but not hands, because like I said earlier, hands are really complex and they exert forces on things that are hard to measure. And so what excites me is really taking the dexterity thing seriously and to really harness, I'm fascinated by the brain's ability to control a hand and interpret this barrage of signals from the hand. And, the proof is in the pudding with bionic hands. You have to understand how that stuff works to make a bionic hand work. And that's what excites me, is to try to just improve that aspect.
So the brain interface, quickly on the status quo technology is sort of invasive embedding
Yes.
of electrodes or electronics in the brain, right? Are there any approaches that is non-invasive, anything magnetic, anything along those lines?
Let me piss off a bunch of people and say, no way. I just, there's all kinds of extracranial approaches out there, EEG, even the ones that are intracranial but outside the dura, like ECOG. And there, the signal that you're picking up, you're basically listening in on the aggregate activity of hundreds of neurons, thousands of neurons, right? And it's like trying to make sense of 1,000 conversations based on the waxing and waning of the voices, and that's all you have. And I just don't think there's any way that's ever going to be good enough, and I think ultimately these invasive technologies are going to be the way to go. And you know what? I got my PhD in psychology, You know what I mean? I did not do a neurophysiological experiment until my postdoc at Hopkins. And yet I can do these surgeries myself. And I've never killed, they won't let me do them on humans, but I do them on monkeys. I've never killed a monkey during the surgery. All these monkeys have been completely fine afterwards. And if I can do it, professional neurosurgeons can do it too, right? And so this is it sounds worse than it is. And if it worked really well, people would, now let me say some crazy stuff to end this thing. You can cut it out if you think it's too crazy. But as these interfaces, we're reading signals up from the brain, we're writing signals back into the brain through electrical stimulation. As these technologies improve, they can go beyond rehabilitation. I mean, what I work on is rehabilitation for amputees and spinal cord injury patients, right? But once you can do that really effectively, you can start really interacting with extracorporeal devices with the same flexibility that we can interact with our own muscles and our own senses. This really kind of opens a whole realm, of possibilities. Imagine, for example, this is my favorite one. This is the one I wish I had, right? And I'm not going to have it in my lifetime, but maybe, my grandchildren. If you could interact with the whole of human knowledge with the same flexibility that you can interact with your own kind of semantic knowledge base, you could, that was part of your knowledge, you would become an altogether different organism, right? And that's the kind of thing that we can dream about. If you think about how fast technology and science is evolving now, that's the kind of thing that we can dream about in, a century or something. And that's sort of, we're taking the first step towards that.
Yeah, I mean, brain enhancement, that would be sort of the natural progression. But that, I guess along with that comes a bunch of ethical and regulatory complications. But
it's a total mess, a total mess. But you know what? The thing though is, and we think about this and we have meetings about this, like, okay, what do we need to be, vigilant about? But you can, we just need to be prepared because, like the whole amount of we're not going to say, okay, this is dangerous, let's stop, right? This is going to march on. And what we need to do is be prepared to face the ethical challenges that are looming. And there are some, like, here's the classic one, right? The classic one is, as you start enhancing or, augmenting yourself with hardware, is there a point where you stop being a human being and start being something altogether different? And, probably, but is that a bad thing? I don't know.
And then you can be hacked. Right now our computers get hacked, and then our brains get hacked. Yeah.
That is a thing that, there's like a thing about the Elon Musk thing that I don't get, is that he's building these devices, these implantable devices to interact with devices to fight off the singularity. But it seems like if you had a, malevolent AI, the last thing you want is for it to be able to hack your brain directly. Anyways.
I agree. I think, even AI area, people are just too optimistic. And humans have always been too optimistic about when things are going to happen. It will happen, but it's going to take 10x number of years than we typically forecast, I think.
I'll take your word for it. I don't know. I think there's a lot of variation on opinions on that point. Some people think are terrified because it's looming, and not just, people off the street, but actual AI people. And other people are like this is ridiculous and there's nothing to worry about.
Excellent. Yeah, this is a great area. Great area for emerging students to get into, right? Graduate students. So where does this sit at University of Chicago? You say biology and anatomy. So what is the department that this area sits in?
Oh, yeah, right. Well, so I'm in the Department of Organismal Biology and Anatomy. As you may or may not know, I saw that you had one of my colleagues from UChicago in your last podcast. But, the UChicago, like, for instance, neuroscience is distributed over a bunch of different departments. So we have some neuroscientists in the Department of Neuroscience. Actually, it's the Department of Neurobiology. But we have some neuroscientists in statistics and physics, and several of them are in my department, the Department of Organismal Biology and Anatomy, which is a biology department. that is really kind of, it's called, I didn't know what organismal biology was until I joined the department, but it's a department that really focuses on kind of organismal level questions. So I study the entire sensory system and its interaction with the motor system, for example, right? And my colleague Nico Hatsopoulos is an expert on the motor system. Dan Margoliash, an expert on the auditory system, etc.
Excellent. Yeah, this has been great, Sliman. Thanks so much for spending
time. Yeah, this was a lot of fun. Thanks a lot.
Thank you.